Okay, so for our Fibonacci formula on Mathematica, A is going to be, I'm just defining some variables. A is the square root of 5.
Yep.
B is 1 plus A over 2. C is 1 minus A over 2. And Fn is 1 over A, so 1 over root 5, times B to the n minus 1 over root 5 times C to the n.
Okay.
And so I'll just evaluate that. So now that's created my function. And you know what? Just to save a little room and make it easier for the camera, let's get rid of that output. So now I just want to do what's F0? What should that be?
Should be 0.
Okay, and it is.
F of 1.
F of 1 should be
1.
1. Uh-oh.
Well, well, is that 1? Is the question.
Okay. Is that 1?
Well, we can just add the two terms together and we get 2 over... Oh no, hold on. So it's going to be 2... No, it's 2 root 5 over 2 root 5. So that's...
Yeah, there's a little minus sign
Yeah.
right there.
That is 1.
Yeah, so maybe I need to change my formula here and tell Mathematica to simplify. And now what does it say F of 1 is?
1.
Alright. Sometimes Mathematica doesn't simplify unless you tell it. So F2 should be?
Also 1.
Indeed.
3 should be 2.
F3 should be 2. F
4 should be 3.
F5.
5.
6 should be 8.
What is that?
7 is 13.
But here's the amazing thing. We can now calculate the 30th Fibonacci number without calculating all the rest of the ones before it.
Oh, that's cool.
Yeah, so we have found an explicit formula for the Fibonacci numbers. Or I could calculate the 100th Fibonacci number, which would really take quite a long time,
Yeah.
doing the recursive way. And yet there it is.
Cool.
And one of the reasons I wanted to do this is we were talking about recursive functions yesterday. But a second reason, just by an incredible coincidence, I saw our friend Nassim Taleb, working through a problem last night on Twitter. Of course, my computer doesn't have it displayed quite right. He was working on a problem, and let me show you the problem first. It's up here. So suppose you repeatedly toss a fair coin until you get 2 heads in a row. What is the probability that you stop on the 10th toss? Do you think this problem has anything to do with the Fibonacci numbers?
No.
It doesn't look like it.
Sure doesn't seem like it at the beginning. But her friend Nassim Taleb was playing around with this, and he used some basic Markov chains. Remember when we did a Markov chain?
Yeah.
So he did some Markov chains, but the interesting thing is he got this formula for the stopping time at time x. Is that displaying okay?
Yeah.
Yeah, hopefully. 2 to the 1 minus 2x times 1 minus root 5 to the x, 1 plus root 5 plus negative 1 plus root 5 times 1 plus root 5 to the x, all over root 5. Now when you see, after our project today, when you see that expression, do you think of the Fibonacci numbers?
Yes.
A little
it's
bit.
Pretty.
It looks similar to our expression that we found.
Yeah, it's a little bit hidden, but you do have that constant 1 over root 5 on the bottom.
Yep.
You have 1 minus root 5 to the power instead of 1 minus root 5 over 2, and 1 plus root 5 to the power instead of 1 plus root 5 over 2, but you have these extra powers of 2 over here. So you bring those inside, and all of a sudden, you arrive at a formula that looks a lot like the Fibonacci formula. And sure enough, overnight, I might have to zoom in here. That's probably going to cause some serious focus issues. So never mind. Sorry about that. Let's zoom back out. Oh, too bad. Now I'm out of focus. Oh, so much for the end of that video. Anyway, it turns out that you do get the Fibonacci numbers. And so the stopping time at time 10 is the 9th Fibonacci number divided by 2 to the 10th, or 34 over 1024.
Yeah.
Isn't that amazing?
Yeah.
So it's funny, I was thinking about doing this project last night, and then something with this explicit formula for the Fibonacci numbers just showed up on my Twitter feed.
Cool.
Which is really neat.
Yeah.
Bring that back into focus. Okay, well good. Good work this morning, guys. High five. Good job.